Good morning, Stockholm. How are you?
Good evening.
They're not awake yet. It's too early in the day. Hello, good morning.
Hello. Hello, good evening.
Well, good evening, that's right. Good afternoon.
Yeah, exactly.
Guten Abend. I don't speak Swedish. I don't speak German either, but I know a few phrases.
Even we don't know Swedish, so it's okay.
All right, very good. Stockholm, we're going to give you the honor of asking the first question today. What question do you have? If you don't have a question, it's okay, but if you do, this is your big chance. Well, I don't.
Excuse me, can I ask? Can you hear me?
Yeah, sort of.
So I had this question that when we are solving for the divergence in the second homework, when we are getting the eigenvalues, there is also it turns out to be sine of lambda L, which is equal to 0. So there is also a solution which is corresponding to the integer 0, that is sine just 0, where everything turns out to be 0. So it is basically the solution when there is no flow in the system. So does it have any other physical significance?
Does anyone get that?
Yeah. When you solve for it, so
yes.
additional solution is homogeneous solution.
Yes.
Yes. But it's not significant.
I still don't understand the question. Can you say that again?
When you find the coefficients
Yes.
of the solution.
Yes.
So one of the possibilities is sine equals 0.
Yes.
So yes, if there is a significance for this solution.
You understand. You answer the question because I don't understand the question.
Guys, can you ask again?
Okay.
Guys?
Hello? Stop. Again?
Okay. Hello?
Yes.
So when we are solving for the divergence, then we have a lot of eigenvalues which corresponding to the solution of the equation sine of lambda L equal to 0. So here we use the equation that the argument of sine, it should be equal to n pi. Okay. So for using it equal to be n pi, there is also a solution corresponding to n equal to 0.
Yes.
So in that, the Q divergence turns out to be 0.
Yeah, I hear that.
Okay.
One thing you need to check after you find the eigenvalue is to compute the eigenfunction. And you'll find in some cases there will be degeneracy. That is, even though you get an eigenvalue, the corresponding eigenfunction itself is 0. And I think that's what happens in the case when n equals 0. Did I get that right?
Yeah. So does it have a physical significance that it is only the case when there is no flow or something else?
Well, that's right. When there's no flow, I think on a physical basis you can understand there can't be divergence if there's no flow. But I think what will happen in the mathematics, in the mathematical model, you'll find that when you substitute that value of the eigenvalue, you will find that the corresponding eigenfunction itself actually has to be 0. Also, sometimes you end up, in order to formulate for some of the eigenvalues, you end up with when the denominator of a trigonometric function is 0, the numerator is also 0, so we have 0 over 0. And you have to use something called L'Hopital's rule. I don't remember how to spell it. Yeah. When you have an expression where there's a numerator and there's also a denominator, and they both are 0, so you end up with 0, then you have to apply this rule in order to know what the actual value is. So, yes, there are some special cases, and you have to be careful. That's the real answer. Does that help?
Yeah, thanks.
Okay, thank you. Other questions from Stockholm? Hearing none, I will turn to our distinguished gathering in Durham, North Carolina. Are there any questions in Durham, North Carolina?
I have a question about it's more like, what's the answer?
What's the answer? Well, you have to wait until the answer is posted.
Like I'm struggling with
You're struggling. Well, that's when you learn, when you're struggling. If it comes easy, then you don't learn anything. So be of good cheer. That means you're learning something. Yeah. But do you have a question short of asking what the answer is?
I mean, yeah.
Which part of you, there are several parts. Which are you struggling with? The equation of motion or solving the equation of motion?
Part where you
Have variable GJ?
Yeah.
Well, maybe this will help. I don't expect you to be able to work out all the values of those integrals. There are going to be some integrals, right? You can't work them out unless I tell you what GJ is and how it varies with Y. So you have to leave the answer in terms of integrals. That's all you can do. Still is a problem?
Well, I don't know. I will try to
Think about it some
It's
more.
good. It's good that you confirm that.
Okay, all right. But don't expect to be able to work out all the integrals because you have to be given GJ or E or C to know that, right?
Yeah.
And that's, now that you're experienced aeroelasticians, that's left for your assistant to work out the integrals. Unless I ask you to do so. Yeah. Yeah, right. Right, okay. All right, well, today, what shall we talk about? We can talk about one of several things. I made a list. In fact, let me show it to you. We can talk about the beam rod. By beam rod, I mean we're going to take our wing and let it bend as a beam and twist as a rod. So we'll have both bending and twisting of the wing. We can do that. That's one of the standard models people use in aeroelasticity. We can just skip over all that and go directly to the plate. And then the beam rod is a special case of the plate. And a plate model is pretty general. It's not the most general model you use, but it's pretty general. We can talk about modes in general because what happens in practice is the structural model is really the following. There's a structures group over there. They have a finite element code. And you say, run your finite element code and give me the natural modes of the wing, the natural structural modes of the wing. I'm an aeroelastician. I don't do that. But I know that's your job. You do that for me. Well, you're nicer than that because they are doing your favor. And so they produce the modes. And then you can write down the kinetic and potential energy of the wing in terms of those modes. And that's where you start. And so it's important for you, if you're going to work in aeroelasticity, to have some awareness of the kinds of structural models that are out there. But there are plenty of people who understand structures who don't have a clue about aeroelasticity. And so there's no point in your replicating their expertise, right? So we could do that. But orthogonality is important because the natural modes that are produced by the finite element group have this wonderful property called orthogonality. And almost always, but not always, but almost always, those are the modes that you're going to use to derive equations of motion that you'll use in a flutter analysis or other aeroelastic analysis. And then finally, in fact, I'm now going to ask you a question, and also our friends in Stockholm. At least within the framework of linear aeroelasticity, it's important to understand the theory of dynamics of linear systems, which is usually a separate course all by itself. So I'm going to give you the short form of that course. We're going to cover that course in 1 or 2 lectures. But that presumes that you have some exposure in some course previously to the dynamics of linear systems. So I'm going to ask the group here in Durham first, and then I'll ask the group in Stockholm. Has everyone had a course in the dynamics of linear systems at some point? I have. Did you raise your hand? Okay, fine. All right, Stockholm, I have consulted our group here in Durham, and they claim, we'll find out if that's true or not, of course, they claim they understand the dynamics of linear systems and have had actually a course in it. How many people in Stockholm have had a course or at least some significant exposure previously to the subject of dynamics of linear systems? Would you raise your hand so I can get a sense?
I would say just 1 or 2 people.
Okay, fine. All right. Well, then I will cover the dynamics of linear systems. I will not charge you anything extra for doing this, but and I will perhaps not go quite as fast as I had planned to before I saw that raising of hands. So, but you need to slow me down. You need to ask questions if I go too fast. Okay?
Okay.
Great. All right. Now, so the question before the House this morning is, do you want me to continue and talk about structural modeling per se and orthogonality? I can do that. Or I can cover dynamics of linear systems today. We're going to do both. It's just a matter of which order we're going to do. Do you have a preference here in Durham, North Carolina?
I want to see the plate, but
You want to see the play, okay. Anybody else have an opinion one way or the other, or a preference?
should if we do the plate, then we'll have the beam rod and shit.
Special case. Yeah, you like to do that, huh? Of course, what I'll do then is I'll assign the derivation of the beam rod from the plate theory as a homework, right? Just to make sure you understand, all right? That's okay. Well, you walked right into that, didn't you? Okay, but you'll learn something. Okay, Stockholm, what we're going to do, we would give you a say, but the vote here is so overwhelming. We're going to talk about plate theory today, and then I'll point out to you that the beam rod model is a special case, and then we'll assign you a homework problem, which is to show that. And then the next lecture, or maybe depends on how long it takes us to go through plate theory. The next lecture, the next topic after that, will do the dynamics of linear systems. In the meantime, those of you in Stockholm who have not, or anyone really, including the folks here in Durham, who have not previously looked at the subject of dynamics of linear systems, it's covered in chapter 3 in the book, right? So look at chapter 3 and read that. If you don't understand everything you read, it's okay. That's why you're taking the course. If you understood everything you could read in the book, we wouldn't need to have the course. You just read the book and whatever, right? So my lectures are to enable you to read the book with some greater understanding. Okay, so we're going to talk about plate theory today. We can do that. Plate theory. And let's draw a picture of a wing again. We can draw it like this. And now, thank you. And now I'm going to think of the deflection of any point on that wing where we have an x-coordinate and we have a y-coordinate. The deflection at any point I'll call W. That's the deflection normal to the paper. It depends on x and y, of course. And since it's dynamics, it depends on time. But we're not going to assume that there's an elastic axis. We're not going to do that, at least not for this development. the deformation could be fairly general. In fact, just to emphasize that point, let me draw another picture. Here's another wing, right, which perhaps looks more like a real wing. Looks like a wing that somebody's testing the wind tunnel, right?
Except the trailing gauge is straight.
Oh, I see. Okay. By the way, just as a preview of coming attractions, Danny Levin has built a wind tunnel model, and he's doing some preliminary testing to make sure it's really going to do what we want it to do. And then those of you in Durham will go down and actually see it in the wind tunnel. And those in Stockholm, unfortunately, we can't bring you over. Our budget doesn't allow us to fly you over for the laboratory demonstration, but we'll make a video of it. In fact, you think we're going to do a streaming video. We're going to actually do it live to Stockholm?
Yeah.
We hope so. So we're going to have a laboratory demonstration sometime the next week or so. Anyway, okay, so this again is W, a function of X, Y, and T. Okay? All right, so now the question is, how are we going to represent this structure? And I'm going to show you how it's really done. And we've been doing some simpler models, but now we're going to do what most people do most of the time with real airplanes. So this is one. So here's what we do. We take W, a function of X, Y, and T, and we do what we've done before. We express it as a summation of modes, if you will, a generalized Fourier series, where we have some coordinates which depend on time, and we're eventually going to write down some equations for these, which we will try to solve, right? Times some carefully chosen functions of X and Y. And those functions are the functions that the finite element group is going to produce for us from some structural model and one of any number of finite element codes. There's Nastran and Abacus and ANSYS. And there's just a zillion companies out there that'll sell you a finite element code. Okay. But then, as we know from our previous discussion of Hamilton's principle and Lagrange's equations, we need to be able to, we're going to represent the structure, we need to be able to write down kinetic energy and potential energy, right? Okay, so the kinetic energy is easier, so I'm going to start with that. Kinetic energy is 1/2. It's always 1/2. That's the part I always remember. And then it's the double integral over both X and Y of the mass per unit area, which may depend on X and Y, right? Because the mass may be distributed in some way. And this, in principle, includes concentrated masses if you want to use delta functions. But if you want to, you can just for the moment think of it as a smooth function of X and Y. Times the velocity. The velocity is dw dt squared dx dy. Okay, so I better give these equations some numbers. Now, Neil, this is much clearer today than it has been sometimes in the past, right? Don't you think? And I'm using pencil. This is good stuff. Okay. Okay. Now, so let's take equation 1 and put it in 2 and see what we get. We'll get 3. It's going to be 1/2. This m is the mass. This m is the mole index. Never to be confused with each other, right? But this is often what people use in the literature, so bear with me. So I'm going to have m, x, and y. And now I'm going to use a dot to denote time derivative because it'll make my writing a bit easier. So I'm going to have the summation over m, qm dot psi sub m squared dx dy. But as I mentioned before, when you square an infinite series, it's better to write it as one series with one index times a different series with a different index. Otherwise, the bookkeeping gets confusing for me. You would never have a problem with this, but I do, and that's why I prefer to do that. So we're going to write this again as 1/2 the integral of m of xy summation of m qm dot psi m times summation over some other index n qn dot psi n dx dy. All right? Or collecting everything and recognizing that the QMs only depend on time, and so they can be taken outside the integral. And of course, the summations can as well. I can write this as 1/2 summation over m, summation over n, qm dot, qn dot, times what's left, right? And what's left is the mass per unit area times a product of mode shapes. But I prefer to introduce some notation, which is what people use, where m sub mn is defined to be what I need it to be to make this a true statement. Thank you. It's defined, 3 lines means it's a definition. You can't argue with the definition. Well, you can, but assuming that I haven't been careless, it's hard to argue with the definition. It's the double integral of the mass per unit area times psi sub m, which depends on x, y, right? Psi sub n, which depends on x, y, dx, dy. It's just it's a set of numbers. It's really a matrix because it has a double subscript. So I can also write this in the following way. I can write as 1/2 qm dot times a matrix m sub m n times qn dot. Now, you may have to think about your matrix representations, but this is how it's actually written in the computer code, right? It's a product of 3 matrices. It's a row matrix of these coordinates times this mass matrix, which is a square matrix, if you will, times the column of the Q dots. So these are all T's. This is all still kinetic energy, right? So that's pretty easy. That's pretty easy. Okay. Now, I'm going to pause for questions. Are we okay so far?
I have one question.
Oh, okay. Yes, Stockholm, yes, do you have a question? And I'll come back.
Yeah. So, in the modes we are taking, I'm not sure if, let's say, if we have a torsional mode or if we have a bending mode.
Yes.
Yeah. So then, which mode is which we should take there, or I'm not sure.
Yeah, I think you're asking me which is bending and which is torsion in this representation. Is that your question?
Yeah, that's the question.
The answer is you don't know yet, but you're going to find out when you do the homework that I'm going to assign to you.
Okay.
Okay. But so far, this representation doesn't even assume that there's an elastic axis. There may be, there may not be. If there is, great. If there isn't, that's okay too. In this representation, it doesn't matter. All you know is that these structural analysis people using their finite code produce some modes. Now, if you're experienced or even not so experienced, you can look at the modes they produce and you might be, by eye, be able to identify that one looks like it's mostly bending and that one looks like it's mostly torsion. In a real airplane wing, there's hardly ever an elastic axis, unless it's a very simple wing. But nevertheless, people still, partly for historical reasons, say, oh, that's the bending mode. Well, it's not pure bending. It's mostly bending with a little something else. And that's the torsion mode. Well, it's not really all torsion, but it's the torsion mode with some other stuff. So people like to talk in terms of bending mode and torsion mode sometimes, even for relatively complex wings, but they're not pure torsion. They're not pure bending. Whereas the beam rod model assumes that it's either pure bending or it's pure torsion, right? It's one or the other. But that's an idealization, like a straight line, right? There aren't any straight lines, but sometimes it's a useful idea to think about. Okay, so that's kinetic energy. You had a question. I answered it. Good. That's good. All right, now we're going to write down potential energy. Okay, you ready for this? Here's the potential energy. It's 1/2. Q sub m, not Q sub m dot, Q sub m. K sub mn. Q sub n. Well, that was easy. Of course, it does leave open the question, what is K? And the answer is it depends. First of all, it could be some matrix that the structural analysis people just give you. And you say, thank you very much. And if you have confidence in them, sometimes you do, sometimes you don't, you move on. But what you might tell the structural analysis people is, I want you to produce the eigenfunctions, the natural modes of this system, in which case I know what this matrix is. It's the following. So special but very important case. Of eigenfunctions these are the structural mode eigenfunctions or natural modes. Of the structure. In that case, U is this. Well, no, I won't even bother to write it again. I'll just tell you what KMN is. KMN is equal to omega sub m squared, m sub m. Those there are two m's there. Oh no, yeah, right. Delta of mn. Delta of mn means it's 1 if m equals n, okay, and otherwise it's 0. So this is then just a diagonal matrix. Each diagonal element is the value of this coefficient, m sub m, right, when m equals n, times this quantity omega m squared. What's omega m? It's the natural frequency. And why is this an important thing? Because someday, before the airplane flies, someone's going to take the structure and shake it out in the laboratory and measure the resonant frequency. And then the moment of truth will arrive, and you'll see if the measured natural frequencies equal the computed natural frequencies. And it's a good day if they're close. It's a bad day if they're not. Okay? Either someone screwed up the design or someone screwed up the calculation of the natural modes. Neither of which is a good thing. Probably better they did a bad job on computing the natural modes than the design itself was bad, right? But either one is not a good thing. Okay. But nevertheless, if it's a good day and everything comes out properly and the measured values are pretty close to the calculated values, then you move on. So that's a simple thing. Now,
excuse me, Prof.
Yes.
Can you explain another time what the term, the circle term is? Is a delta and n?
This is the Kronecker delta.
Okay, makes sense.
Yeah.
Is delta n n?
Yeah, it's 1 if m equals n, and it's 0 if m does not equal n. And it's usually called the Kronecker delta. Okay?
Okay, thank you very much.
You're welcome. Okay. So that's it. Hey, we covered all of linear structural analysis, at least for aeroelasticity purposes, in one page. Hey, that's very efficient, don't you think? But again, it's probably worth your knowing a little bit more than this. Not that you, as an aeroelastician, will ever do much of this, but unless it's a small group, right? But if you're working with Boeing, you're not going to be doing this more than likely, or Airbus. But nevertheless, you want to be able to know enough about what those people are doing so that when they give you nonsense, you recognize it's nonsense and tell them you need to straighten that out. Okay. So we're going to now go back one layer more. We're now going to do plate theory per se. Okay, plate theory. We've already discussed what you need for kinetic energy. I'll write it down again. It's 1/2 double integral of the mass. This is the mass now. W dot squared dx dy. And let's see, I should go back and let me put another. I'm going to call, let's see, I'm going to call all of this equation 4 and all of this equation 5. That's just giving some numbers to the equations. You'll see this in the notes. So let's see, this is equation 2 again. And then equation 7, I'm going to cheat and look at a reliable reference. I'm going to write down, what I'm going to do is I'm going to write down an expression for u in terms of an integral involving w, right? Yeah, I sort of skipped that part, didn't I, up to this point, but I'll reveal that much. And I just happen to have a reference here, which I hope still has that expression. There it is. It's the following. It's 1/2, I always remember that part, double integral over x and y, of course, of a quantity called d, and I'll just tell you what d is. This is a representation of the stiffness of the plate, times, and I'm going to use some compact notation, w sub xx squared. What do I mean by w sub xx? I mean it is the second derivative of w with respect to x. That's the notation, right? Plus w sub yy squared plus 2 nu is Poisson's ratio, times w of xx times w of yy plus 2 times 1 minus nu of w sub xy. It's xy, one derivative with respect to x, another one with respect to y, squared dx dy. Where again, and then I won't bother to write down the other ones. I think it's fairly obvious what they mean, right? Oh, I'm sorry. Okay, that's what it is. All right. And so if they were using plate theory, if the structural finite element people were using plate theory to find those modes and find the natural frequencies and all that, they had somewhere in their code this representation, which they then converted into finite element form to do their calculation. Okay. Now,
The expression for D.
I'm sorry again?
D.
What do I need?
Expression for D.
What is the
D.
Oh, D. Oh, I'm sorry. It's D. I'm sorry. Yes, thank you. D. What is D? It's the modulus elasticity of the material times the H, which is the symbol traditionally used for thickness. You might think you'd use T for thickness, but remember we use T for time. So here they don't use T usually, do different ways. It's the thickness cubed divided by 12 times 1 minus nu squared, which is the Poisson's ratio, right? So this is usually called the plate bending stiffness. And you might say, well, what about torsion? Well, see, in plate theory, you just have bending in both directions. You don't really distinguish between one direction and another. Whereas in beam rod theory, there's a span, which is bending, and then twisting is taking place about that axis. But in plate theory, this presumption is it just bends equally in both directions, which it does in general. Okay. Now, what can we do? What can you do? Because I'm not going to do this because it's too much work for me. And I've done it before, so I haven't done it once. I'm not inclined to do it again. In fact, I may have done it more than once. We can use Hamilton's principle and these two expressions to derive a partial differential equation which governs W and the corresponding boundary conditions. And there'll be boundary conditions in two directions, right? Because I have a plate, and so I have to. So if I have a wing like this, I have to have boundary conditions along here and along here and along here and along here, right? I have to have boundary conditions along all the edges. And by the way, it turns out there's special boundary conditions at points, corner points, which come out of the theory as well. One of the famous mistakes in structural mechanics was someone did derive the governing PDE, the governing partial differential equation for W, but they didn't use Hamilton's principle, and they made a guess or used some method to determine the boundary conditions. They got it wrong. When they got the boundary conditions wrong, particularly for free edges, right? As opposed to clamped edges would be sort of obvious what the boundary condition. Free edges is not so obvious. And so they got the wrong answer. This went on for several decades until someone finally pointed out that they've been using the wrong boundary conditions. But anyway, we can use Hamilton's principle and derive the governing plate equation. And I'm going to do that for you. What a good guy, right? It's but I don't remember it. Well, I'm not going to be too good because the only version I remember is the case where D is a constant. That is, I'm assuming that where D does not depend on X and Y. In general, it will, right? Because the modulus probably doesn't change, or it could if this wing were made of multiple materials. But certainly in most real wings, the thickness is a function of X and Y, right? But for the special case, D not a function of X and Y, the governing differential equation is D del 4 W plus M W double dot equals 0. Of course, we've left out the aerodynamics. We haven't put the aerodynamics in. We have to do that later, right? But right now, we're just concentrating on the structural model. Del fourth is, del squared is the Laplacian, and del fourth is usually called the biharmonic operator. It doesn't really matter what you call it, but del fourth is an operator on something, and it's the fourth derivative with respect to x plus the fourth derivative with respect to y plus, I guess, 2, the fourth derivative twice with respect to x and twice with respect to y, right? Oops, sorry. It's got to be, just from symmetry of the operator, it's got to be the same in both the x and y direction, right? You can't really change it. I mean, if I called the x-axis the y-axis and the y-axis the x-axis, the form of the equation shouldn't change. Okay. By the way, this term is actually correct even when m depends on x and y, as it turns out. But, okay. Then, what else? I could tell you one more thing about this. what if we really want to do the beam rod model? Well, first of all, we have to look at a wing that has an elastic axis, right? So the simplest, there is an elastic axis representation of swept wings, but it depends on the swept wing. And it's almost always an approximation that's a further approximation beyond what you have in a straight wing. So I'm going to draw this as a straight wing. So here's why. I'm going to call that the elastic axis. And we are in the beam rod model, we're going to assume that all the torsion, all the twisting takes place about that axis. And then we'll call this the x-axis. And I'm going to measure x from this point. I'm going to measure it from the elastic axis, which will simplify my representation. So the beam rod model is just a plate model, but with a special form for W. So W, a function of x, y, and t, will be written as minus h of t. H doesn't depend on anything other than time, but it's the bending of this axis. You know, it's up and down. And by W, by tradition, is positive up, H is positive down, hence the minus sign. Minus alpha of t, that's the twisting. Also might depend on y. Got to put that in. Oh, I forgot about H. H can also depend on up. I got too excited. Let me do this again. X, Y, and t equals minus H. H can actually vary with Y as well as t. Thank you. Minus alpha, also a function of Y and t, times X. So what's happened is, you see, we now have a very explicit expression in terms of X, which is the simplification of the beam rod model over the plate model. So if you take this and put it in those expressions for kinetic energy and potential energy involving W and work it out, you get the beam rod model. Actually, what you'll get if you do that is you'll get some extra terms beyond what is usually included in the beam rod model. And you'll have to rationalize that they can be neglected, which they usually are, but you can imagine cases where neglecting the terms that come out of this formulation might not be all that wonderful an assumption. Okay. All right. So now you're ready for the homework assignment, right? You're about to hand in one that your reward for doing one homework is you get another assignment. So this is homework number 3. Derive expressions for t as a function of h and alpha, and u as a function of h and alpha, starting from plate theory. Okay, and let's see. I'm going to call this. Well, I'm going to give this this is a nice equation, so let's give it a number 2. That's 8. That's the plate theory. I've already given you the part of your homework answer, so you'll know when you get there. This I'll call 9. Starting from plate theory and equation 9. And then derive the governing PDE, which is that's equation 8, and the boundary conditions for plate theory using 2 and 7. those are the expressions for kinetic energy and potential energy in terms of W. Okay. Well, I'll keep you busy for a few days. And again, as I say, if you really end up in the aeroelasticity group, you'll probably never have to do this again except for this course, but you should know enough that you can, when you talk to the structured people, you can pretend like you know more than maybe you really do, or at least you know enough to ask them intelligent questions. Okay. Maybe the last thing I should say is if we go back to these representations for T and U, within the framework of linear theory, those work even if this plate is a plate with beams going both ways called stringers and what's the other thing? Stringers and chordwise. Stringers is not your problem. I think that's all I really want to tell you today about the structural theory. We could start a discussion of dynamics, but I'm more inclined to wait and do that on Thursday to start fresh. Right?
Excuse me, we lost last minute due to problems.
Say again?
We lost the last minute.
Okay.
Oh, you lost it last minute. You want me to tell you, say it again?
I mean, if there's anything important, we would like to know it.
What I said at the end was I was thinking about whether I should continue on and start talking about linear system dynamics or just stop here, since that's quite a different subject. Well, let me do this. I think what we heard today in terms of linear system dynamics is that the group here in Durham has had some exposure, but our folks in Stockholm have not. But there's one thing is to understand linear system dynamics. The other thing is to understand the mathematics that's used to do that. So we're going to talk about Laplace transforms. We're going to talk about Fourier transforms. We're going to talk about random vibrations, power spectral density, correlation functions. So are all of those terms familiar to the group here in Durham? Some of you know, some of you. There's a really nice course in linear system dynamics. You can get an entire semester of this if you want to. Stockholm. How many of you know about Laplace and Fourier transforms?
I would say almost everyone.
Well, if you don't know about it before, again, when you start reading chapter 3, you will gain an appreciation. The good news is, if you have had exposure to sinusoidal motion in time, which I hope you have, and you've had an exposure to Fourier series, then Fourier integrals are a natural evolution generalization of Fourier series. And Laplace transforms are a special case of Fourier transforms. So when we do our discussion of linear system dynamics, we're going to start out with Fourier series, which I hope you heard about, and then we'll go from there, and from that we'll evolve to Fourier series, and then to Laplace transforms, and then finally we'll use that same mathematical apparatus to discuss random vibrations. It's a very powerful set of tools and well worth knowing about because it's of use not only in aeroelasticity, but in almost any kind of system, whether it's chemical or electrical or mechanical or whatever, that has dynamic systems behavior. And that includes a lot of engineering and science. Any more questions before we stop for the day? I'm sorry?
In equation number 9, how does the thickness h depend on time?
Could you try me one more time, please?
Okay.
Please ask the question one more time.
No, in equation number 9.
Number 9, okay.
Number 9, okay.
So,
Yes?
h is the thickness of the plate or something else?
He wants to know what H is? Yeah. H is the bending of this axis. I'm sorry. H is the bending of this axis in and out of the paper. And the minus sign comes about because H is taken as positive down while W is taken as positive up. This is just a matter of convention. I mean, you could use another sign convention, but because of that sign convention, that's the minus sign. But if this wing had no twisting, but only had bending, then H would be the entire story. But because it also has twisting about that axis, this term also gives rise to displacements at other points on the wing as well. Does that help?
Yeah, thanks.
You're welcome.
Prof, I have another question.
Yeah.
In the homework description, you wrote derive the governing PDE from equation number 8, right?
Yes?
Can you show me again which equation number 8 is?
Which one 8 was? Yeah. 8 was this expression. This is going to be the governing PDE that you will derive by using the Hamilton's principle, starting with expressions for kinetic and potential energy. And it'll be somewhat lengthy, but it's good exercise, right?
Okay, thank you.
There are people in the world, relatively few people, who've done that. So you'll be among the select few. In fact, I would suggest you ask your friends and neighbors who are not taking this course if they've done this, and you'll say, you missed a great opportunity. Okay?
Professor, I have one question.
Yes.
So when we talk about orthogonality of modes,
Yes.
I'm confused as to how. My questions are always about bending and torsion, but I'm confused as to how I can understand how bending modes are orthogonal to each other because they are all sine, and when I mathematically try to multiply two signs of different things and try to integrate with respect to 0 to L, I get 0 and 1. But how are like bending, torsion, and twisting and edgewise they are all orthogonal?
Okay, let's talk about that because, that's a good thing to talk about. We have a few minutes. Let's talk about orthogonality. Let me talk about it for the plate first because although if you actually do the calculation, it's more complicated than for the beam rod, conceptually it's easier to explain. So let's first of all look at the plate and then we'll look at the beam rod. Plate. And all of this is orthogonality. For the plate, there are actually two orthogonality conditions. There's one involving mass and one involving stiffness. Okay? So with the mass, the orthogonality condition is as follows. Remember, these mode shapes depend on x, y, too. that's equal to 0 if m does not equal n. It's equal to something other than 0. It's not 0 if m equals n. And you might ask, well, what does it equal if m equals n? The answer is anything you want it to be. Because the mode shapes are only defined within an arbitrary constant. And so often what people do is, remember the total mass of the wing equals just the integral of the mass per unit area, dx dy, right? That's some number. That's the total mass, call it m. So often you would scale these modes so that when m equals n, this integral is equal to the total mass. That's convenient. Another possibility is you could scale the mode so that the maximum value of the mode is 1. That's another common way to do it. But the truth of the matter is you can do it any way you like. And sometimes you'll read a report where someone's used a really personal, idiosyncratic way of normalizing modes. So you got to be careful, because some people may defy conventional wisdom and choose their own way of normalizing. And that's very important, this conversation between you and the people who give you the modes, right? How did you normalize these modes? Because they don't tell you, But anyway, so this is an orthogonality condition. Obviously, this simplifies things because a lot of terms are 0 when all the terms when m does not equal n, right? The orthogonality condition involving stiffness of the plate is interesting and much more elaborate. I could assign that as a homework. Maybe I'll save that for the final exam. Anyway, there's another orthogonality condition for the. I'll tell you, it involves d, right? And involves an integral over x and y. But it's much more elaborate. Now, with respect to the beam rod, you ask, what about the beam rod? So remember what we're doing here. We're assuming that W equals minus h of y and t minus x of alpha of y and t, right? So there are some modes associated with H-type motion, and there's some other modes associated with Y-type motion. And in the beam rod model, they're independent of each other. Okay. So but nevertheless, this is still true, right? Because what I'm about to write down is a special case of this. But more specifically, then, if you have the I'll call them the bending modes. You will have an integral like this. It's the mass per unit area times C, which will then, this is the chord, right? So this will give you the mass per unit span when I multiply by C, times HM of Y, HN of Y, dy. This will be 0 if M does not equal N, and it'll not be 0 if M equals N. Okay? And for the torsion modes, this is almost too good to tell you. It would be much better to assign it as a homework problem. I won't do that. It'll be the integral of I alpha. You remember what I alpha is? It's the mass moment of inertia about the elastic axis, right? Times alpha m alpha n dx dy equals, and so forth, right? It's 0 if m does not equal n, and it's not if m equals n. And now the equations for orthogonality for the stiffness are simple enough that I remember them without trying to derive them from in detail. It's EI. This is not the mass moment of inertia, right? This is the area moment. Sorry about that. Remember the mass moment has I sub alpha on it. And sorry, but this is the notation people use. I can't help that. I didn't invent this notation. Times second derivative of h with respect to y m, second derivative of h n with respect to y dy equals 0 if m does not equal n, and so forth. And then there's a corresponding gj d alpha m dy d alpha n dy dy. But the point is that the orthogonality, because it's a beam Raman, the orthogonality conditions for the bending modes and the torsion modes are separate and distinct. But again, these orthogonality conditions could be derived from the orthogonality condition for the plate model under the special assumption that W has this form that can be written in terms of H and Y, right? Or H and alpha, excuse me. Then the question is, where did they come from? Okay, I usually do assign that as a homework problem. Okay. So I'll tell you where they. Well, I'll tell you. Let me go back to the torsion. Remember, we did torsion, right? You derived. Let's just think about torsion. You derived an equation of motion for torsion that looked like this. And again, we've left out the aerodynamics, right? This is just the structural model. You recall this, right? Okay. So where did this one in particular and the corresponding one for involving I alpha, where did those come from? Well, we know that each of the natural modes in torsion, and there's a counterpart to this in bending, each of the natural modes in torsion, alpha of y and t is equal to alpha m of y e to the I omega mt, where this omega is the natural frequency associated with the torsion. And you could put a super alpha up here to remind yourself that this is a natural frequency associated with the torsion mode, and there are also some natural frequencies associated with the bending mode, right? But the two different sets of natural modes and two different sets of natural frequency. If I I don't know if I should number all these. Well, let me go back and number all these equations. So this is 10. This is 11, 12, 13, 14, 15, 16. Oh, we're on a roll here. 17. If I take 17 and put it in 16, right, I'll get minus omega sub m alpha squared. That's from the second derivative with respect to time. I alpha sub m. There's going to be an ei omega t in both terms. I'm going to cancel those out. Plus d dy of gj d alpha m dy equals 0. That is, the natural modes must satisfy the difference equation of motion, right, at the relevant frequency. Then, so this is the mth equation. There's also a similar equation for any other mode. Call it the nth. Yeah, thank you. The nth equation, which I won't bother to write down again. Okay. Now, if I want to prove this, what do? I multiply the mth equation by the nth mode and integrate with respect to y. I multiply this equation by the nth mode and integrate with respect to y. If I do that, then if I subtract these two equations in a clever way, either the stiffness or the inertia terms will cancel, and whichever one doesn't cancel, I'll prove orthogonality for the other one. And then I'll manipulate the equations another way and get the other orthogonality equation. You ever seen anything like this? I'm looking at the people in Durham, North Carolina. It's sort of vaguely familiar, right? If you took boundary value problems and learned about Sturm-Liouville theory and all that good stuff, that's what this is. That's what this is. So anyways, the important point I will leave with you is that starting from the equation of motion, you can, from those, prove orthogonality. And by the way, you can prove orthogonality for the general case, where Gj depends on, in this case, on y, and I alpha depends on y. It turns out the proof of orthogonality is as easily done for the case where you have variable properties as is for the case when you have constant properties. The only thing that's simpler about the constant properties, if you actually want to compute what the modes are, it's a lot easier to do it for the constant property case. But just to prove orthogonality, it doesn't matter whether you have variable properties or not. The proof is just as hard or as easy. Stockholm, did I tell you more than you wanted to know about orthogonality?
Yeah, that answers my question.
Why don't you just go back to one? Either way, someone would have been in trouble. Okay, let's stop here. Unless there are other questions. Any other questions here in Durham? Hearing none, we are adjourned.